All right, so we have covered pretty much the bulk of Chapter 2. There's nothing really left except for two ideas. Those two being relative motion, which is not as useful a concept until Chapter 5, and absolute dependent motion, which you will see a lot of, particularly in the next chapter. But today we're covering relative motion. One of the things I did want to sort of emphasize today is this is what we've covered so far. We have covered all of the coordinate systems that we will be using in this course. X, y, and t are theta. And we have, at this point, defined position x, y in the I and j vector directions, s for an nt, which is just a magnitude, and position for an r theta, which is r, which is equal to the magnitude of r in the r direction. Velocity is, again, rate of change with respect to time. It's easiest in the Cartesian system, and it's vx, vy, vz. And acceleration is acceleration x, acceleration y, acceleration z. And one of the questions that I saw over the weekend is, why do we write certain things the way we do? And so when it came to nt, it was okay, v equals vet. But acceleration is a combination of the acceleration, the rate of change with the magnitude of velocity, and the rate of change of direction. And so at is equal to at, which is dv dt. An is v squared over radius of curvature. Radius of curvature being rho, and defined there. Where it gets a little bit more complex is there's always a feeling that r dot should be v. It isn't. So v is equal to r dot plus in the er direction plus r theta dot in the e theta direction. So both of these are component parts, and it comes from the fact, again, the complexity that's introduced with this coordinate system, hello. Yeah, it'll come in a second. There we go. And I'll just give it some scratch down there. So, by the fact that we have derivatives on these unit vectors. And so in order to actually describe velocity in r theta, we need to have r dot and r theta dot. And finally, more importantly, acceleration in the r direction and acceleration in the theta direction also have additional components. And again, these are coming out of your derivatives on your unit vectors. So when you calculate the derivative of this and the derivative of this, you'll have an ER term that appears, and that is where you get that minus r theta dot squared. And you'll have an twice r dot theta dot that appears from the derivative on E sub r. All right. Which leads to this. I can define distances from an absolute origin. So I have an origin here. I have an xy coordinate, just as usual, xy, origin over here. But I can also define a second origin, which is or axes, which is translating. So I'm going to call that a translating reference. And it's going to be x prime, y prime. Now, it's oriented the same way, so I'm going to have x prime parallel to x, y prime parallel to y at this instant. But I can sort of define things. So in this case, it's actually RB with respect to A. These are all vector terms. And all that means is, if I want to sort of describe R sub B, I could just say R sub A plus RB with respect to A leads me to RB with respect, or RB. So I can write out that out. So I can say the vector sum of r sub b equals r sub a plus rb with respect to a. And the notation I'm using is such that every time I write it like that, these terms should cancel, essentially. And when they cancel, I get the term of interest, so r sub b. Nothing exciting about that. If I take the derivative of that, I end up with VB equals VA plus VB relative to A. I can again take another derivative on that, and if I do it, I get the acceleration. This then leads into a class of problems that involve planes and boats flying off in different directions and solving for relative velocity of one with respect to the other. It's not terribly interesting in this part of the course. So I'm going to do a couple examples at this point to sort of talk about them. But we will largely, I think I do one more example in Chapter 3. But in Chapter 5, this is the crux of the course. In Chapter 5, these sorts of relationships suddenly become the velocity of b is equal to a translation plus a rotation. And this becomes very important at that point. And if you have geometries, you can start to describe what's happening in those cases. But they're not as interesting at this point with particles. Again, sort of out of some of the comments, on Piazza, it's possible to solve these graphically. If you're very good with doing scale drawings, you can do a really good job. Generally, I do not. I use trig. And what I do is I just project them into each of their component parts. So just sort of an understanding, if I take this equation, I can write RBX equals RAX plus RB with respect to AX, RBY equals RA y plus RB with respect to AY. Both of those, or that's sort of the better solution method of the two. You may, again, you may be better with a protractor than I am, but I just can't do it. Okay, one thing I forgot to mention at the beginning, I have posted onto Quarkus my OneNote for all of the lectures 1 through 6 on Wednesday or Thursday, depending on how much energy I have Wednesday night. I will try and post 1 through 8, and then I'm not going to do anything until much later when I do particle kinematics. I'm making a modification to sort of include the lecture videos in the OneNote, so that's sort of where I'm at. So this is a typical problem. The driver of car B sees a police car P and applies their brakes. causing the car to decelerate at a constant rate of 8 meters per second squared. At the same time, the police car is traveling at a constant speed, velocity of the police car of 50 kilometers an hour, and using a radar gun. The police officer sees B coming at them at 120 kilometers an hour when theta is equal to 27 degrees. So there's theta, you see velocity P, you see velocity B, and you'll notice that this deceleration is occurring in the negative sense. At the instant the radar gun measurement was taken, determine the corresponding true speed of B and the magnitude of the relative acceleration of B with respect to P. Now, not clear maybe, I have a bad habit of not putting my axes down right away, but it's good to put your axes down. I'll maybe not this direction. Maybe why this way? It's always important to remember or vaguely remember how you wrote your axes. Velocity of B is equal to the velocity of P plus the velocity of B relative to P. Same thing as before, and these are vector terms at this point. So the velocity of B relative to P is equal to velocity of B minus velocity of P, and I'm going to try and keep vectors separate. Velocity of B in the I direction. All right. All right, so they're both there. Actually, no, that's not correct. Okay, this is the correct. I need to write my axes at the beginning of the problem. Okay, so that ends up being velocity of the driver versus velocity of the police car, but velocity of the driver in B is negative. There we go. So I have that. I have all of that information. I do have the relative velocity at 27 degrees. Ooh. Now, I can define a unit vector that points along the line from the police car to the driver, and that's E B with respect to P. So I have a unit vector. That unit vector is going to be E B with respect to P equals to sine theta plus cos theta I and j. Now I know one other thing that I'm not going to get from the math, but as the driver is moving to the left, the line between P and B gets shorter. So, That is, if you can imagine, and this is where you got to do visualization, as that approaches 90 degrees, or 0 degrees in this case, the distance between B and P shrinks. And if that's the case, you can solve through and say velocity of B is velocity of the radar minus velocity of the police car cos theta over sine of theta, which is equal to 182.7 kilometers an hour. Don't drive that fast. But it is kind of useful to realize you can do a lot of these things. And the really tricky bit here is this idea that the unit vector is going to define everything for you. So it defines sort of a secondary coordinate system, and it kind of worked out really well. Now, this is where it also happens that the acceleration of B is to the right, which is my positive direction. So acceleration of B with respect to P is equal to acceleration of B, which is 8 meters per second squared in the I direction, minus 0. So it ends up being pretty straightforward in this case. So you're looking at still very complex kinds of motion. I mean, this is kind of, you can imagine there's a lot of things happening here. But you're able to sort of pull out some pretty good results from that. Any questions? This one right here. So, velocity of the radar. Should I have done one other thing? Just check, make sure. Oh, I just wanted magnitude. That's where I made a mistake. So I dotted that. It's just the velocity of B with respect to P is only going to act on that one line. So the measured velocity is only, or the radar gun is only measuring along that line. It's not measuring any other component of velocity. So in order to sort of pull that out, I do the dot product. It gets rid of the normal component right away. Okay. Let's see if I can get a better one. More car problems. All right.
Wait,
Sorry. Well, 1, 2, just hold on.
going back to that, what we asked, is the reason why it's negative because velocity is pointing in the opposite direction as the radar?
So it's negative because as you rotate around, so if I look at the car and my elbow, both the car, the police car, and the driver are coming closer to each other. So V sub r is decreasing with time. So the length between the two is decreasing. So I have two cars coming together, and it goes like this. So it eventually, hopefully they don't sort of collide together, but there you go. B is going fast enough, they'll go right by there. It'll be easy for the cop to catch them. Go ahead.
Along which unit vector is the radar pointing?
So the unit vector for the radar is this one right here, because that's what you're measuring. So as the person is rotating around or coming closer, the radar is sort of catching another bit of the person.
You said that when you dot this unit vector, you
So that's the unit vector B with respect to p. And what you're measuring is the normal component of that velocity. So you're measuring the velocity in that direction, and you're measuring two velocities. You're measuring this one, and you're kind of measuring that one. And what we're really extracting, that's the direction you're at. And you're only really seeing a displacement along the distance between the two. So that's the one you're interested in. It's a complex geometry.
Since the unit vector and the velocity of the radar are pointing in the same direction, shouldn't the velocity of the radar just equal the velocity of B with respect to P right away?
But that's the velocity of B.
With respect to
No, that's the velocity of B.
what I'm saying.
So this is this is velocity of B. This is the velocity of P. They're both moving with different directions at that instant. You're measuring a component of velocity as you approach the car. It's one of the reasons why when you're sitting on the 401, the police officer is not usually oriented normal to the 401. They're parallel to the direction of traffic. So this becomes a lot easier to do for them. This is a funny case, and it's a particular case looking at a geometry that's a slight bit more complex than what you might be used to. Okay? The important point here is that the measurement, or the velocity that you're measuring, is the one that is defined by that unit vector. We're doing a lot of unit vector work, and that's where we're going to go with that. Go ahead.
If our unit vector is pointing from P to D, shouldn't our velocity B with respect to P be negative?
B with respect to
It's
P.
pointing in the opposite direction.
Yeah, it is actually. So velocity, I've put it as a negative value. So both of, this is one I probably will regret giving, but there you go. It's a good one to sort of look at. It's a good one to try afterwards. The geometry and sort of looking at these kind of cases is kind of okay. It's fun. Maybe I'll do this one. No, I'll do this one. This is similar enough that maybe I'll have less trouble with it. All right, here you're not measuring velocities. You have two velocities here. Car A is accelerating in the direction of its motion at a rate of 1 meters per second squared. Car B is rounding the curve at 140 meters at a constant speed of 50 kilometers an hour. So this is similar, but not the same as a problem you're doing in the homework. Determine the velocity acceleration that car B appears to have to an observer in car A if car A has reached a speed of 70 kilometers an hour for the positions represented. All right, 140 meter curve, 30-degree angle, X and Y are shown there. X is positive to the right. You have a curved path over there. Okay, so starting point's the same as ever. You're going to start with this fundamental equation: velocity of B equals velocity of A plus velocity of B with respect to A. If you want the speed of A, it's 70 kilometers an hour, which, if you do the conversion, is 19.4 meters per second. Velocity of B is 50 kilometers an hour, which is equal to 13.9 meters per second. Okay, so we have from that the two component parts, velocity of A, velocity of B. We have not done anything in terms of breaking it up into component parts, but we have directions associated from the drawing. So, if I have velocity of B equals to velocity of A plus velocity of B with respect to A, the way I would like to solve this is to use my components. I've drawn out there the two velocities. So velocity of B, if you complete the triangle, is acting at 60 degrees, acting downwards, 13.9 meters per second. Velocity of A, 19.48 meters per second. So velocity of A plus velocity of B with respect to A will give you velocity of B. So velocity of Bx equals velocity of Ax and velocity of By equals velocity of Ay plus velocity of B with respect to Ay. Okay, I just want to keep that showing. So, different ways of approaching the same problem, but I can write this out in this form right here. And I'm going to, is that good? No, I'm going to keep that up. No, I'm going to go over here. All right, so if I take both of these equations down here, velocity of B with respect to Ax is equal to velocity of Bx minus velocity of Ax. So I just want the component parts. Velocity of Bx is velocity of B cos theta minus V sub A x, which is V sub A, sorry. Because V sub A is traveling horizontally along the x-axis. There. Same thing. Velocity of By, or B with respect to A in the y direction, is just going to be the y component velocity of B, because the y component velocity of A is equal to 0.
Oh, sorry, I'm just wondering if it's for VB cos theta, is it supposed to be 60 degrees or is it?
It's 60 degrees. Yeah. Oh no, sorry. It's this. Yeah, it's 60 degrees. Oh, they're days. No, that should be 30. Yeah, that should be 60. This is equal to 30. Never do trig in your head. Okay, so now you have all of that. You have all of the information you need. V sub b cos theta, V sub a sine theta, and you end up with V sub b a in the x direction, which is minus 12.5 meters per second, and minus 12.02 meters per second. I'm gonna keep Now, for the acceleration of car B, you're told it's at a constant velocity. Car B is traveling with a velocity of 50 kilometers an hour at a constant rate, but it is traveling along a curved path, and that curved path has a radius, of 140 meters. So acceleration of B is equal to 13.9 meters per second squared, all over 140 meters, which equals 1.38, 1.4 meters per second squared. So you can calculate the acceleration of B with respect to A in both component directions using the relation at the top. Acceleration of B with respect to A is AB minus AA. Calculate AB with respect to AX, AB with respect to AY, and you end up with acceleration of B with respect to A, which is equal to the magnitude of both, which is equal to 0.716 meters per second squared. And from this, we can go back to triangles. And you can say acceleration of B with respect to A over sine of 30 is equal to acceleration of B over sine of beta. Beta is equal to inverse sine 1.38 over 0.716 sine of 30 and you end up with beta equal to 105.7 degrees. For beta. You also have sort of the complementary angle, which is going to be 74.3 degrees if you carry it out to a whole bunch of significant figures. Go ahead.
How come for the acceleration of B, we only use the Earth normal component?
So for the acceleration of B, we only used the normal component, because when the problem was stated, we were told that the car B is traveling along the curve path at a constant rate. So if it's traveling at a constant rate, the acceleration tangential, I might as well sort of go back to my first slide. So if I'm dealing with this, acceleration tangential is equal to 0, and the acceleration of this is an in the en direction, which, if you remember the problem, is pointing in towards the center of curvature. So as much as possible, and this is, next week we're going to be talking, or next week we'll be doing the quiz, try to remember what the various definitions are. So yes, you can put them in the crib sheet. Yes, we already have provided you one crib sheet. School's crib sheet is kind of interesting, but I have corrected at least one or two things on school's crib sheet, so be very careful with that. But it's useful to sort of write things out. The other nice thing about that or writing a crib sheet now is today you can prepare a crib sheet that's 2 pages long for relatively little information. By the end of the course, you can fill in the whole thing. So I would start working on the crib sheet as a useful study tool. And that's kind of what the intent is with it. Please don't go into the exam having never looked at the crib sheet you're using. That's dangerous.
If the acceleration wasn't constant in the tangential direction, right, will we then create like its own triangle and get its nets?
Exactly. So say, for example, I changed this problem so that B was accelerating at 1 meter per second squared. I would then have a component of acceleration acting in this direction that I would add into my triangle. And so one of the questions that came up, I think you guys had somebody asked why they could do the velocities. This problem, it wasn't, well, it's kind of like this problem. I kind of like this problem because it's similar, but it's sort of flipped. Why they could solve it in xy coordinates and not r theta? Well, the reason is there was an error in the r theta coordinate components that they calculated. Because in the end, all we're doing is this. Velocity of A plus velocity of B equals velocity of B with respect to A. It doesn't matter whether you're using xy coordinates, r theta, and t. They're always going to be the same final result. So over the weekend, on Friday, I posted a new video on YouTube where I just solved a projectile problem, and I did all parts of it. So I did Cartesian coordinates, I did nt, and r theta. It's the important point in all of this is that no matter how you do these things, you do not change the total magnitude. So every time we solve these problems, remember, you're not creating 3 different solutions to 3 different problems. If it's the same g, it's always going to have an acceleration g. It's just the component parts will have different values.
I'm just confused about this drawing here. So is BB with respect to A always perpendicular to BB?
Is it always perpendicular? No, it's not perpendicular. Oh, in this case it is. Okay, in this case it kind of worked out nicely. But not always. And in chapter 5 it'll get a lot more complex in terms of the shapes.
I'm just a bit confused. How do you like the angle between B with respect to A? And
So-
BB is 90.
So how did we know VB with respect to A? In this particular case, I kind of knew it from dropping a perpendicular in here, so it worked out. Sometimes you get lucky. Okay. So it's not always going to work out that way. Sometimes it's going to be, and the reason why it sort of worked out in this particular case is because this is a horizontal velocity. Now, the other case that might have happened is a vertical and a horizontal velocity, which you'll see a lot. And in those cases, you also have this. However, since you asked, and it's your own fault, let's look at a different case where you don't end up with a 90 degree. So I have shore-based radar. And it indicates that a ferry is leaving its slip. So it's just moving out. And as it moves out, the velocity of the ferry is 18 kilometers an hour at 70 degrees. And instruments aboard the ferry indicate a speed of 18.4 kilometers an hour and a heading of 30 degrees west of south relative to the river. Determine the velocity of the river. So, so now you have velocity of the ferry, you have velocity of the river. So velocity of the ferry equals velocity of the river plus velocity of the ferry relative to the river. Now you're given at the beginning of this problem that this is 18 kilometers an hour. This is equal to 18.4 kilometers an hour. And you're given, I'm going to try and draw this without red crayon, I guess, that this is 70 degrees and this is 30 degrees. And here I have 18.4 kilometers an hour. 18.4 kilometers per hour. And this is 18 kilometers an hour. This angle is 10 degrees. So I know that because I'm given all the information at the beginning. It's 30 degrees west of south, which tells me south is here, 30 degrees over gives me that distance. And it's going out at 70 degrees with respect to the slip. And so there's the difference between the two is that 10 degrees. So now I have a diagram where the only missing bit is the velocity of the river. So velocity of the river is equal to velocity of f squared plus velocity of f with respect to r squared minus twice velocity of f, velocity of f with ferry with respect, and cos of 10 degrees. Ew. Okay. I should have written down, there are a whole bunch of law of sines. I've already used law of sines here. You're going to use law of cosines a lot. There is a law of tans. I usually sort of delay sort of introducing them, but you've seen them in the past, I'm sure. But when you're dealing with triangles, that's what you're going to end up using. So I know velocity of the ferry with respect to the river. I know what velocity of the ferry is. I don't know what velocity of the river is. I know what cos of 10 degrees is, so I can get everything I need. That's alpha. Okay, velocity of the river is equal to 3.1974 kilometers per hour. And another question that came up on Piazza is how many significant digits do we need? I strongly suggest that as you're doing problems, you just keep whatever you have. Your precision is okay on a calculator. You're going to do okay with that. When I give a solution like this is a terrible solution. I should really write something like 3.2 or 3.2. If you're worried about this, giving an answer like this, what I would do is I would write both answers. I would say, here's my full, don't go crazy, don't write 10 digits, okay? Just 4 digits is going to be plenty. But then you write the next line down, you say, look, it's 3.2 kilometers an hour. That's a reasonable sort of step to take. I'm going to keep writing it that way. And then when you give the direction, you can give the direction in this form. Now, to be honest, I've kind of solved this as a full vector solution. I probably would have been better off just breaking it down, and I haven't done the calculations, into x and y coordinates and leaving it as an ij. And I could have done that. That should, once you have those two pieces of information, you know everything that you need to do. In x and y. Either solution is correct. If you don't want to mess around with vectors, it's better to go with coordinates. Go ahead.
Can you explain the logic of how you know that the river, how you got the directions and the velocity arrow of the river compared to the instruments in the ferry?
So I was given the velocity of the ferry, and I'm given the velocity of the ferry with respect to the river, right?
They said the instruments on board, that's with respect to.
That's right. So it's with respect to, so I'm measuring from a ground station, and I'm measuring from the ferry itself. So I'm getting the velocity of the ferry relative to the river. That component, that measured velocity on the ferry, is the measured velocity with respect to the river, because the river is pushing it at the same time. So you can see that in the end, this is what you end up with, because you're pushing in one direction and you end up being pushed by the river at the same time. So it's really important to sort of break it down into these types of approaches.
Sorry, I'm just confused about the final rule.
Yeah. That's alpha. And then the 17 is coming off of just sort of doing a 90 on this. So just bring it into the horizontal.
If you could go back real quick.
Back to,
Yeah, you said 18.4 on the B with respect to R.
oh, sorry, yes, that is correct. That's how I should have written it. Thank you. Okay. I got 15 seconds. Any other questions on this? Because I'm not going to start a new one. Then tomorrow or Wednesday, I will talk about absolute dependent motion, which makes much more sense in a particle problem than this does. But we will deal with this.